Right. So this is the start of the presentation on set theory. This will be the first one. So set theory is one of the most important topics which will be covered, as it is basic for any other topic that should be studied further. First of all, the first definition: a set is a collection of different elements. Uh, Normally, if you have the same elements, you would use the word collection rather than set. And in the case that you would be talking about sets of sets, it's also better to use a family of sets or a collection of sets. Avoid using the word group, as this one can be associated with group theory. And now we present a few examples of sets. We have the set 0, 1, 2, 3, and 4, which is obviously a set. The set R, which is a set which encompasses all the real numbers. The set Z, which is a set which encompasses all the integers. And this last one is written in a set builder notation and represents all those x which are natural, such that x is less than 5. We will be using the convention that natural numbers start from 0. So in this case, the last set is equivalent, is the same set to the first set. Now we present the most important sets. The natural numbers, which are all the numbers 0, 1, 2, 3, 4, and so on. The integers 0, 1, negative 1, 2, negative 2, basically all the naturals and their additive inverses. The rationals, which are those numbers which can be expressed in the form a over b, such that a and b are integers and b is not 0. In other words, all those numbers which solve a linear equation. Now we also have the reals, which I have not included their definition, as it is slightly hard for this introductory course, and it will be done using something called Dedekind cuts, which are too advanced. The complex field are all those numbers of the form x plus yi, where x and y are real numbers. This last one is called the empty set, which is a set with no elements. One thing that we say about this set is that it is included in all of the sets, which will explain what it means later on. Sets also have operations. The two most basic operations are union and intersection. The union and intersection are represented as shown. The second symbol is usually used to represent multiple unions, sometimes even uncountably many. The same for the intersection. If we have x being any set, then we would have that lowercase that if we have some number x in n such that x is less than 5 and work out its intersection with another set which is x in n such that x is less than 3, we would have the sets 0, 1, and 2. This is because those are the three elements which are in both sets. The union of the naturals and the negative natural numbers, bearing in mind that 0 is natural, would yield the integers. Intersection between the real numbers and the complex field is equal to the real numbers, as after all, the real numbers are subsets of the complex numbers. The union of the real numbers and the complex numbers is equal to the complex numbers, as all the real numbers are complex numbers after all. Here we also have, for the next one, we also have a strange symbol, which is IR, which represents those numbers created by multiplying the imaginary number by the real numbers. In other words, all the imaginary numbers. The intersection between the rationals and the imaginary numbers is actually 0, despite the fact that it says there the empty set. And the intersection between the empty set and some set x, which was defined before, is equal to the empty set. We also have that the union between for the empty set and x is equal to x, as After all, we're adding a set with 0 elements to some sets, so it's not adding nothing. And this last one is a little bit harder, but represents the intersection of those of sets of naturals, which would be in this case 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. The symbol to the left, which might be a little bit hard to understand at first, represents the the natural the intersections for infinitely many intersections. Bear in mind that if in this one I forgot to include that 0 is natural, which is a slight mistake. This intersection, if we wanted to visualize it, would be the intersection of this set with with the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on, with following by adding the number in front ahead. And now, before defining the complement, we have to define a subset. A subset x of y, written as x subset y, is a set such that for all x, that symbol there means for all, the upside down a, is a member of x, and x is also a member of y for all of them. Of course, this is not a proper subset. It's just any subset which might be equal to the set. For example, we have that the empty set is a subset of 0, 1, and 2, which, if you wish to prove, can be proven vacuously as for any x in the empty set, in other words, no x will also be in 0, 1, 2. Then the set 0, 1, 2 is a subset of n, which is a subset of the integers, which is a subset of the rationals, which is a subset of the reals, which is a subset of the complex, which is a subset of the complex. Again, it's important to notice that the symbol represents the any subset, not complex, not proper subset. As if it represented proper subset, the last the last part of it would not be true. The complement of a set X over the universal set, which is which could be any set, in fact, is expressed as XC. Similarly, the set difference of two sets, Y and Z, is expressed as shown. There are two possibilities. I generally prefer using the second one. If we take the universal set to be R, and say two sets X and Y are members of the real numbers in the real field, such that the complement of X equals Y, then the complement of the reals is the empty set, and the complement of the empty set is R, and the complement of Y is equal to X, as X is the complement, as the complement of X is Y. Combining these, we can get a very famous result. These few operations, we can get a very famous result. De Morgan's laws. The unions of in summary, this would be that the complements of unions are intersections of complements. Complements of intersections are unions of complements. This basically this is what is said there. However, in a more easier to understand, in an easier way to understand. So if we have some sets, it doesn't matter if the amount of sets is finite, countable or uncountable. We take the complement of all of their unions. We get the intersection of the complements of each of the sets, and the same thing with the taking the intersections and then the complements. Now, if you wish to prove this, we can consider x to be in the left hand side and show that x is in the right hand side. Therefore, the left hand side would be a subset of the right hand side. Similarly, consider that x is in the right hand side and show that x is in the left hand side. The right hand side is a subset of the left hand side. And the right hand side can only be a subset of the left hand side, and the left hand side be a subset of the right hand side, if the left hand side and the right hand side are equal. So this is how you would prove the De Morgan's laws. I have not stated the whole proof, as I do not, as I do not think it's very constructive when you once you get the idea. I think the idea is more important. So we now introduce the field actions. These are the actions which define certain sets of elements named fields. So the way to define them would be by generally I like to set them into in the 5 additional axioms and the 5 multiplication axioms and then the distributivity axiom. So let's call this field F, and then we have that any field is closed under addition. That basically means that if you add any two elements in the field, they will stay in the field. In any field, addition is associative. If you add 3 elements, it doesn't matter which order you add them up. In any field, addition is commutative. If you it doesn't matter if you do a plus b or b plus a, you will get the same result. There exists an additive identity 0 in all fields. And that basically means that that number, when added to any other number, will still do this, leave the number the same way. So x plus 0 is 0 plus x, which is x. Any number in a field has an additive inverse. That means that every number has a negative in a field. So 2 has its negative, negative 2, and so on. This is why, for example, the natural numbers are not a field. The multiplicative action, the first multiplicative action, is basically the same, but for multiplication, any field is closed under multiplication. Second one, in any field, multiplication is associative. The third one, in any field, multiplication is commutative. The fourth one, there exists a multiplicative identity, one which is not 0 in all fields. This is really important, as there is a very some people think that the set consisting of 0 only is a field. However, it does not have a multiplicative identity different from 0, as the multiplicative identity is the same as the additive identity, which should never happen in a field. Finally, we have the fifth multiplicative uh, axiom, which says that any number in a field which is not 0 has a multiplicative inverse. If it were 0, it does not have a multiplicative inverse, as we have 1 over 0, which would not make sense. And in some examples, it does, like in the extended reals, but those are not fields after all. We also have the distributivity axiom, which means that multiplied by b plus c is equal to ab plus ac. If a, b, and c are members of the field. Now we present the definition of an upper bound U. An upper bound is any number for which, given a set, which is x, for example, equal to x1, x2, x3, x4, x5, x6, all the way up to xi, where I missed the braces, but anyways, all the xi, so all the elements are less than or equal to the upper bound. Similarly, a lower bound L is any number for which, given that that set X, all xi are greater than or equal to L. The lower bound and the upper bound could be in the set, or they could not be in the set. It does not. Both are possibilities. For example, if we have the set 0, 1, 2, a possible upper bound would be 10, as it is greater than all of the elements in the set. Similarly, a lower bound for that set would be negative 10, as it's lower than all of the elements. As a primum is the lowest value u, such that for all xi, I is less than or equal to u. Therefore, for example, we have that for the set 0, 1, 2, the supremum would be 2. And This is the only supremum, as any other value would not be the greatest supremum, as the lowest supremum, as the lowest upper bound, as there are lower ones. The supremum does not necessarily have to lie in the set. For example, if we have the set of numbers lower than the square root of 2, then the supremum is obviously the square root of 2, which is not in the set. Similarly, an infimum is the greatest value L, such that for all xi is greater than or equal to L. Therefore, we have that in the set of numbers greater than or greater than the square root of 2, the infimum would be square root of 2. These are the most important, and some theorems about infimums and supremums, which are important to know, are for example, for any finite set, we have that the infimum and the supremum must necessarily lie inside the set. However, for infinite sets, we might have there is a chance that they do not lie in the set. All right, so this is the end of the set theory lecture, and we will next time it will be on the basic topology that is needed for analysis. Hope you enjoyed.